Hi everyone, welcome to CAIE Science, and today we will be solving the remaining questions of May June 2022 for 429701. Okay, we I think we did 5 questions right in the first part, and now the organic chemistry starts from question number 6. Okay, part A. The reagents and conditions required for nitration of benzene, benzoic acid, and phenol are shown in table 6.1. Okay, the conditions for the nitration: benzene, benzoic acid, and phenol are given to you. Concentrated nitric acid and concentrated sulfuric acid react to generate electrophile NO2 plus. Okay. Complete the figure 6.1 to show the mechanism of the reaction between benzene and NO2 plus electrophile. Include all relevant curly arrows and charges. So now the electrophile is a species which is deficient, which has a deficiency of electrons. Okay. So, and this double bond is going to be acting as a nucleophile, which because double bond has a very large high charge density, so it will the double bonds will attack this electrophile. Okay, so this is your first arrow. This will attract the electrophile, and then what will happen? This double bond will break, and there will be a positive charge, and NO2 plus group will be attached. Okay, now the hydrogen will lose its electron and it will form H plus ion. Okay, so it will form nitrobenzene like this, nitrobenzene plus H plus ion. Okay, so this is the mechanism, and you have to remember all of the mechanisms in this organic chemistry. Okay, write an equation to show the how sulfuric acid is regenerated. Okay, so when the nitric acid reacts with sulfuric acid, concentrated sulfuric acid, they form Na2 plus electrophile plus HSO4 minus plus water. Okay, so the sulfuric acid is changed into HSO4 ion. Okay, now how the this sulfuric acid will be regenerated? The HSO4 minus will react with this H plus ion. Okay, will react with this H plus ion, so it will form sulfuric acid. Okay, part B. Draw the major products from the mononitration of benzoic acid and phenol. Okay, so now you have to see that on which position the nitrous NO2 group will attach in benzoic acid and phenol. So this will be told by you that which group is attached to benzene. Okay, if either 2,4 director is attached or 3 director is attached. So now firstly I will draw the benzoic acid only. So this is benzoic acid, COOH, and this is phenol. Okay, so now you have to see that either phenol is 2,4 director or 3 director. So, and this benzoic acid is 2,4 director or 3 director. So in this syllabus you are required to remember that which one is 2,4 director and which one is 3 director, and you can check by seeing this that if any group attached to this benzene has a double bond, it will be a 3 director, and if any bond attached to the benzene has only has a group attached which has only single bonds, so it will be a 2,4 director. So if you see, there is no double bond in OH. Okay, there are only single bonds in OH. So this will be a 2,4 director. So nitration could be attached. This is carbon number 1, 2, 3, 4, 5, and 6. Okay. So NO2 group, nitro group, can be attached to 2, 4, 6 positions. Okay, mononitration. So I'm attaching NO2 over here, but and the other possibility is that this sorry this nitro group is attached to this and this position. Okay, so these both are possibilities. Okay, these both are right answers. Now this carboxylic group has a double bond. Okay, you can see there is a double bond, so it will be a three director, and this nitro group will be attached at the third position. Okay, so that's how you uh, calculate whether it is a 3 director or 2,4 director, and these will be your major product. Okay. Part C, compare the relative age of nitration of benzene, benzoic acid, and phenol. Explain your reasoning. Include reference to the structure of 3 compounds in the answer. Okay, so which one will be easily nitrated? Okay, so benzene, benzoic acid, and phenol. So if you see, the phenol does not require concentrated uh, nitric acid. It only requires dilute nitric acid and very low temperature, 20 degrees Celsius. Okay, and benzoic acid requires concentrated sulfuric acid, and it has extreme conditions. Okay, it is using higher temperature, and then you have benzene, which also requires concentrated nitric acid and sulfuric acid, but you can see the temperature is low in benzene than the benzoic acid. So you can see from the table that phenol is uh, easily nitrated. Okay, the phenol is easiest to nitrate of all benzoic acid and benzene. Then you have benzene, and last you have benzoic acid. So the trend is easiest. Which one is easiest? Phenol. Okay, then benzene. Okay, and then you have benzoic acid. Now what is the reason? So in phenol, this is your phenol. In phenol, this lone pair on OH is delocalized into the ring. So the electron density of ring is increased. Okay, so it attracts electrophile better. So you can write lone pair on oxygen in phenol delocalize delocalizes into ring. So it increases electron density of the ring. So it attracts electrophile better. Okay, electrophile better. Okay, so this electron density of the ring is uh, increased, so the electrophile will be attracted more. Okay, that's why phenol is more easiest to nitrate, and the nitration of phenol is more easier than the benzene. Okay, and benzene, the the you can say electron density of the ring is lower than the electron density in this phenol. Okay, now benzoic acid on the other hand is a COOH group is an electron withdrawing group, so it will take electron from ring, so the electron density on the ring will be decreased. Okay, so that's why it is less easiest to nitrate benzene than benzoic chloride, sorry, than benzene. Okay, so for benzoic acid, so you can write COO group, the carbonyl group is an electron withdrawing group. Withdrawing group. Okay, so the electron density of a ring decreases. Okay, that's why this uh, this it less attracts electrophile. Okay, the electrophile is attracted less in benzoic acid. Okay, this is your reasons. Part D, the azo compound Tango red is used as an acid base indicator and can be made by the route shown in figure 6.2. This is your figure 6.2. This is your Tango red, this molecule. Okay, so in step 3 of this synthesis, the compound Y reacts with compound Z. Okay, compound Z is made from compound X. This is your X, and assume that this group does not react. Okay, this group is unchanged. Okay, this does not react. Now what it is saying in first part, suggest the structures of compound X, Y and Z and draw them in boxes in figure 6.2. Now is you if we are firstly, let's look at this Kango red compound. Okay, this large Kango red molecule, or you can say compound. So you can see there is an azo group. Okay, this azo group. Okay, now you have to see that as you have to realize that this azo group is made from a diazonium ion. Okay, so there must be a diazonium ion in this Y, Z or X. Okay, now this SO3 Na group is over there, and this group is also in this Y. So, and you can see that these two rings, this is structure is similar to this structure of this your compound. This is given to your starting compound. Okay, so now you can actually say that this molecule and these two molecules are uh, these two molecules can be your Y. Okay, and you can count the number of carbon atoms. So 1, 2, 3, 4, 5, 6, okay, 7, 8, 9, 10. Okay, so there are 10 carbons, and you if you count the number of hydrogen, it will be 8, and there is one nitrogen, and you have three oxygens, and then you have sulfur and sodium. So the structure of Y is, now you have calculated the structure of Y, right? I'm just erasing it. So now you have the structure of Y, which is like this. This is your first ring, then here comes your second ring. Okay, now you will attach amine group over here, and then you have this group. Okay, so this is a test over here. So this is your structure of Y. Okay, now let's consider this structure. Now let's clear this. Now let's consider this structure. Okay, so this will be made from this azo group will be made from diazonamine. So there must be a diazonamine. And how diazonamine is made? It is made from how diazonamine can be made from this nitro group. So firstly you will reduce this nitro group into phenylamine. Okay, you know the synthesis of phenol. Okay, and you know the synthesis of diazonamine. So from benzene. Okay, you know the synthesis of diazonamine from benzene. Okay, so then firstly we will make this nitro group into phenylamine, so by reduction. Okay, and then this phenylamine will be changed into diazonamine. So how uh, this nitro group will be changed into phenylamine? So the structure of X is going to be like this. So this is how you reduce this nitro group into a phenylamine. Okay, so now, and if you count the number of carbon atoms and number of hydrogen atoms and number of nitrogen, so you will see that this compound is correct. Okay, you have to just realize things. Okay, you have and these things comes with practice. Okay, so practice is very important. Now you will how you will make diazonamine? Now you will make diazonamine from phenylamine by reacting it with HNO2, so it will form diazonamine. Okay, now this is your diazonamine plus. And when this diazonamine reacts with Y, it forms this Kango red compound. Okay, so this is your synthesis. Okay, now it is asking for give the reagents and conditions for step 1 and 2. So in step 1, the nitrobenzene is reduced to phenylamine. So how we achieve this? We achieve this by reacting it with tin plus concentrated sulfuric acid. Oh, sorry, concentrated HCl. Concentrated HCl. Okay, plus heat under reflux. This is your synthesis. This is your reagents and conditions for step 1. You have to remember the conditions. Okay, there is no other way, and there is no logic in which I can tell why tin and concentrated HCl is used. You just have to remember these conditions. Okay, step 2. In step 2, this phenylamine is changed into diazonamine. So this diazonamine is stable only under 10 degrees Celsius. Okay, if the temperature is above 10 degrees Celsius, this diazonamine will be very unstable and will break. Okay, so how you make this diazonamine? So basically you react it with HNO2. This is nitrous acid, and temperature less than and equals to 10 degrees Celsius. Okay, and there is also you can also write this NaNO2 plus HCl and temperature below 10 degrees Celsius. This is also correct because, and this is also this is correct because this HNO group is very unstable and it is not directly added. You add sodium nitrate plus HCl, so it forms HNO2 plus NaCl. Okay, so that's how you get HNO2. So these conditions you can also write this. Okay. Question number 7. Okay. State the use of TMS, which is a tetramethylsilane, and D2O, which is a heavy water, in NMR spectroscopy. So TMS is a standard or reference compound. Okay. Standard or reference compound. Now DTO, it is a heavy water and it is used to identify the OH group or NH group, because this DTO group disappears the peaks of OH and NH. So that's how you identify that either it has OH or NH group present or not. So uh, used for identification identification of OH group or NH group. Okay, NH protons. Let's move to this part B. The three isomeric ketones with the molecular formula C5H10O are pentane 2 on, pentane 3 on, and 3-methyl butanone. Now complete the table 7.1 to show number of peaks observed in this proton NMR spectrum and in carbon 13 NMR spectrum for each compound listed. Okay, so let's draw first this butane 2 on. Okay, if I draw butane 2 on over here, this is, sorry, pentane 2 on, this is pentane 2 on. So if I draw pentane 2 on, it's going to be like this. Now you have to see the environment of hydrogen for proton NMR spectrum. So if you see here the environment of hydrogen, if you see how many peaks will be given. So if you see these all hydrogens, they have same environment, right? You can see that. Now let's move to these hydrogens. These two hydrogens have same environment. Okay, and then these two hydrogens will have same environment, and then in last is this will also have a different environment. Okay, so how many environments of this hydrogen are there in pentane 2? There are 4 environments. Okay, so 4 peaks will be shown. Now how many environments of carbon are there for carbon 13 NMR spectrum? Okay, sorry, let's redraw this. Okay, let's redraw. Okay, now let's redraw pentane 2 on for this carbon environment, carbon 13 environment. So this is your carbonyl group over here, ketone group, and then you have these hydrogens. Okay, so now you we have to find the environment of carbon. Okay, so for that you have to see that this carbon has a different environment. Then you have this carbon which has also different environment from this carbon. Then you have this carbon. Okay, this carbon is also a different environment. Okay, so you have three environments, and then you have this carbon which is also a different environment, and at last you have this this carbon which is also different environment. So there are five different environments of carbon. Okay, so five peaks will be shown. Now let's move to pentane 3 on. Okay, so if I draw CH3, CH2, C double bond O, CH2 and CH3, this is your pentane 3 on. So if you see um, these hydrogens, these hydrogens, these hydrogens and these hydrogens have same environment, because you can see that this pentane 3 on, this carbonyl group is attached in the center. Okay, so these two hydrogens, these six hydrogens will have same environment, and then these hydrogens and these hydrogens have same environment, so only two peaks will be shown over here. Okay, so two peaks will be shown in the pentane 3 on in the proton NMR spectrum. And then the environment of carbon. So if you see, these two carbons are in same environment, and this carbon is in different environment, and these are in also sorry, these two carbons are in same environment, and these two carbons are in same environment. So there will be three peaks. Okay, three peaks. Now moving towards last, the 3-methyl butane tool. Okay, so I'm drawing this butane, butane 3-ol. Okay, so butane 3-ol. So this is the structure 3-ol. Okay, CH3. So now if you see here that these hydrogens, these hydrogens and these hydrogen, these all have a same peak. Okay, same environment. So one peak of this, and then this hydrogen has a different environment. Okay, and then at last you have this hydrogens. These hydrogens also have a different environment. Okay, so in total you have three peaks. Okay, now the environment of carbon. So these two carbons have a same environment. This has different, this also has a different environment, this also has a different environment. So there will be a four peaks in carbon 14 NMR, carbon 13 NMR. Sorry. I said all the ketones with the molecular formula C5H10O that have a doublet in their proton NMR spectrum. Okay. So I'm redrawing all of these structures: CH3, CO, CH2, CH2, and CH3. This is pentane 2 on. Then you have CH3, CH2, C double bond O, CH2, and CH3. And at last you have 3-methyl butane. So CH3, CH, CH3, C double bond O, CH3. Okay. This is now you have to see that which one of these has a doublet. So the doublet will be given by a compound which has a one hydrogen on its neighboring, you can say neighboring carbon. Okay, so if you see which, let's consider this one. Okay, this carbon. Okay, if you see the number of hydrogens on the uh, next carbon attached next to this carbon has only one hydrogen attached. Okay, only one hydrogen. So there will be a doublet in this 3-methyl butane, and you have to check others as well. So there is no doublet in pentane 2 on or in pentane 3 on. Okay, there are the two hydrogens in the adjacent carbon, so there will be a triplet, and on this there will be a quartet. So no doublet. Okay, so doublet is only shown in 3-methyl butane 2 on butanone, sorry, butanone. Now singlet, which of these will show singlet? The singlet will shown by the compound which has no hydrogens on the adjacent carbon. Okay, so if you see this carbon has attached to this carbon, and this carbon has no hydrogens attached. So this carbon will have a singlet. Okay, because no hydrogen is attached to this adjacent carbon. So the singlet will be shown by 3-methyl butanone. And if you see this butane 2-on, this also has same environment. Okay, this carbon also has no attached, no hydrogen attached in the uh, adjacent carbon. So this will also show singlet. Okay, pentane 2-on, and there is no singlet in this pentane 3-on. Okay, so these are your answers. Moving towards next part. Okay, cortisone C21, H28, and O5 is a naturally occurring chemical that contains chiral carbons. Okay, reduced number of chiral carbons atoms in one molecule of cortisone. Okay, so now you just have to remember that there will be no chiral carbon on the carbon atom which forms double bond. Okay, and there will be a chiral carbon where there are 4 different groups attached to the carbon. Okay, so now you have to see. Now if I will put a asterisk on the carbon which will be a chiral carbon. Okay, so now this carbon over here is a chiral carbon, and this carbon is also a chiral carbon. You can see that there are 4 different groups attached. Now you have this carbon over here. This is also a chiral carbon, and this carbon is also a chiral carbon. This is also a chiral carbon, and this is also a chiral carbon. So how many 1 2 3 4 5 6? Okay, so there are 6 chiral carbons. Okay, and you can see there are no any other chiral carbons except these. Okay, now the next part, the cortisone is reacted with excess of NaBH4. Okay, so this is a reducing agent. This is a reducing agent. Okay, now state the molecular formula of the organic compound formed. So now this reducing agent, and this will reduce the carbonyl group into this alcohol group. Okay, so now uh, anywhere you found carbonyl group will be reduced. Now let's say this carbonyl group and this carbonyl group, these ketones group, these all will be reduced to OH group. Okay, and this double bond is unchanged. Okay, this double bond will not be reduced. Okay, by NaBH4. So only these groups will be the carbonyl groups will be changed into OH groups. Okay, so there will be an OH attached to this, and there will be a hydrogen over here. Okay, and there will be OH and hydrogen, and OH and hydrogen. Okay, so now you will just have to count number of carbons will be the same, which is C21. then number of hydrogens, this will change. Okay, you have to calculate number of hydrogens. Okay, so you can calculate by your own. 1 2 3 4 5 6. Okay, so 6 carbons, 6 hydrogens are added. Okay, so you have 28 plus 6, so you have 34 now. Okay, 34 carbon hydrogen, sorry. And then you have O5 oxygen, 5 oxygen groups. So this is your molecular formula of the organic compound which will. Okay. Now part 3, cortisone is an optically active molecule. So what is meant by optically active? So optically active means it has a chiral carbon, and it is a substance that is able to rotate the plane of polarized light in opposite direction. So it shows optical isomerism. Okay, so a substance that is able to rotate the plane of polarized light in opposite directions. Okay, so this is your optically active isomerisms. Okay, optical isomerism. Now moving towards question number 8. Okay, compare the relative acidities of ethanoic acid, and chloroethanoic acid and phenol. Okay. So chloroethanoic acid is going to be the most acidic because this has chlorine attached. So there will be a where basically this acidic nature is dependent, which is more acidic, is dependent on the how easily a compound loses the H plus ions. Okay, the acidity depends how easily uh, uh, dissociates H plus ions, and the stability of conjugate. Okay, so these are the factors which show that which compound is more acidic. Okay, so chloroethanoic acid. In chloroethanoic acid, uh, the H plus ions are easy to dissociate. Okay, then you will have ethanoic acid, which is second most acidic, ethanoic acid. Then you have phenol. We will discuss why phenol is more uh, uh, more acidic than this ethanol. Okay, ethanol is least of all. Okay, so now let's see why. So you can see that the acidic nature, acidity is dependent on uh, on how the acidity is dependent on how easily a molecule or a compound loses H plus ions. Okay, H plus ions, and stability of conjugate, and stability of conjugate. Those These are the factors you also have told that this also has a marks. Okay, now you have to explain why this chloroethanoic acid is most acidic. Okay, so in chloroethanoic acid, this Cl um, the chloroethanoic acid has a structure of CH2OH. This is the structure of chloroethanoic acid. So Cl CH2 C C double OH is more acidic than ethanoic acid because uh, the electron withdrawing group electronegative because electronegative or electron withdrawing group electronegative group electronegative group is attached. Okay, so this electronegative group will attract electrons to its cells. Okay, so this OH the bond will be weakened. Okay, now moving towards why ethanoic acid is more reactive than phenol, because this ethanoic acid is more acidic than phenol because electron withdrawing withdrawing effect of carbonyl group. Okay, that's why this ethanoic acid is more acidic than phenol. Okay, and now why phenol is more reactive, because in phenol this lone pair on this oxygen is delocalized into rings, so it will take electrons from the hydrogen, so OH bond will be weakened. Okay, so phenol is more acidic than ethanol due to lone pair of oxygen delocalized into ring. Okay, and in last you can also tell that ethanol is the weakest because in ethanol there is an electron donating group attached. Okay, these alkyl groups are electron donating groups, they will donate electrons to OH group, so this OH group will be strengthened. Okay, in all this phenol, chloroethanoic acid and ethanoic acid, the OH bonds are weakened, and in ethanol this OH bond is strengthened. Okay, so you can also add that as well. Now moving towards part B, an excess of ethanedioic acid, okay, is reacted with warm acidified KMnO4. Okay, state the type of reaction undergone by ethanedioic acid. So this oxidation reaction. Okay, in this your syllabus, methanoic acid and ethanedioic acid. Ethanedioic acid. This is the structure of ethanedioic acid. They both can be oxidized. Okay, so ethanedioic acid is reacted with KMnO4, which is an oxidizing agent. So it is the oxidation type of reaction. With what type of reaction? This is the oxidation reaction. Firstly, now describe what you would observe. Okay, so the color of this KMnO4, it has a color of purple. So the purple color changes into the purple color decolorize. Okay, what will you observe? Okay, the solution decolorize. Okay, the solution decolorize. It initially will have a color purple color, then it will the solution will decolorize. Now write an equation. So the equation is going to be you can use or this oxidation or reduction as necessary. Okay, so this ethanedioic acid reacts with oxidizing agent because KMnO4 is an oxidizing agent. So it forms carbon dioxide and water. Okay, this ethanoic acid is oxidized into carbon dioxide and water. Okay, and this is your equation. Okay, now moving towards next part. Part C, a section of polyester is shown. Okay, draw the structures of two monomers that form this polymer. Now you have to first identify the repeat unit. Okay, so if you see closely, which part is repeating? Um, if I say um, this part, okay, you have to clearly see that which part is repeating. Okay, so you can see that these both parts are same, okay, which I have circled. You can see, so this must be your repeating unit. Okay, so now you have find out the repeat unit. Now let's find out the monomers. You will find monomers from the repeat unit. Okay, so this is your ester linkage. Okay, ester group. So I can say that this part is different and this part is different. Okay, so you will have a monomer and this has O group, so there must be an H group. So this is the structure of first monomer, CH2, C double bond O. Okay, let's make it correct. Let's draw it first here. CH2, C double bond O, H, and then you have OH group. Okay, this is your first monomer. Then you have CH3, and then carboxylic acid group. And then you have alcohol groups. So if you see, if you react both of these, you will get this same um, this same this repeat unit. Okay, you can check this out. If you react these both, you will get the same repeat unit. Okay, so now uh, you can draw these structures. Okay, and by the way, on behalf of this OH, you can also write HCl group. Okay, uh, this is a carboxylic group, and you can also make it a acyl halide. Okay, or acyl chloride. That will also be right, correct. Okay, so now well, I am writing this OH group right now. So you can draw in a skeletal formula because in marking scheme it has given to you in skeletal formula. So you can draw in a skeletal formula, but it is not necessary because it didn't bound us to write in skeletal formula. You can write in any other formula as well. Okay, so these are your both monomers. Okay, part D. Serine can polymerize to form two different types of condensation polymers, a polyester and a polypeptide. And peptide bond has a polyamide group, amide linkage. Draw the structure of polypeptide showing two repeat units. Okay. So the polypeptide has an amide linkage, and amide linkage is this. This is the amide linkage. Okay. The peptide linkage should be shown displayed. Now you can see that this has both carboxylic and amine groups. So this molecule can react with each other to form peptide bonds. Okay, you have to show the two repeat units. Okay, so firstly, this part will be unchanged, CH2, OH, and CH. Then you have this amine group, and then you have this amide linkage. This is your amide linkage, and then you have this CH2, OH, CH, and C double bond O. So now this is your first repeat unit. This is your first repeat unit, and then this is your second repeat unit. This is your repeat unit. This is your repeat unit. Okay, and this is your amide linkage. Okay, so you can show it like this. Moving towards next part. Explain why condensation polymers normally biodegrade more readily than addition polymers. Because in addition polymers, you have a double bond. Addition polymers are made from double bond, and addition polymers don't hydrolyze, or very hard to hydrolyze, very difficult to hydrolyze. Okay, so they are non-biodegradable. Okay, and this condensation polymers can polymerize. Okay, condensation polymers can hydrolyze. Okay, so by hydrolyze you break this amide linkage or ester linkage, but in addition polymerization there is a no such linkage, and there are strong bonds, so it does not hydrolyze. Okay, moving towards next question. Question number 9. The structure of cyclohexylamine is shown in figure 9.1. This is your cyclohexylamine. Now compare the relative basicities of ammonia and cyclohexylamine and phenylamine. Okay, so now you have to first remember that the basicity is dependent on the availability of lone pair and the stability of conjugates. Sorry, so you have to see availability of lone pair. You have ammonia, NH3, cyclohexylamine, and phenylamine. So, and phenylamine has a structure of like this. This is the structure of phenylamine. So in phenylamine, you can see the lone pair in nitrogen is delocalized into the ring, pi electron ring. So this is there is less lone pair is less available on nitrogen, so it will be a less basic than ammonia. Okay, ammonia has lone pair. The lone pair on this phenylamine is will be delocalized into ring, so it will be less available than the lone pair available on ammonia. And in cyclohexylamine, this ring has no double bond, so it is a carbonyl. This alkyl groups will be generate electron donating effect, so they will give electrons to this nitrogen. So there will be more lone pair available to cyclohexylamine than ammonia. So the most basic will be cyclohexylamine. Okay, cyclohexylamine. Okay, then you have ammonia, then this phenylamine. Okay, phenylamine. Okay, and what is the reason? The basicity is linked to ability of nitrogen to donate its lone pair. Okay, donate its lone pair. Now alkyl groups in alkyl group alkyl group is electron donating group. Okay, donating group. That's why in cyclohexylamine, um, this this alkyl group generates an electron donating group, or you can say a positive inductive effect on this nitrogen. Okay, and increase and increase electron density on nitrogen in cyclohexylamine. Okay, then you have this now you will explain on from the respect of ammonia. Okay, now let's explain this phenylamine. Okay, so why phenylamine is less basic than ammonia? Okay, because lone pair from nitrogen in phenylamine is delocalized into the ring into the ring. Okay, that's why it decreases charge density on nitrogen. Okay, so this is your reason. Moving towards next part B. Cyclohexylamine reacts with ethanol chloride. You have ethanol chloride. This is the structure of ethanol chloride. And these acyl chlorides are most uh, reactive series of this organic chemistry. Okay, cyclohexylamine reacts with ethanol chloride to form corresponding amide. Okay, this is your amide linkage. This is your amide linkage. So forms corresponding amide L. Okay, so this is your L. Name the mechanism for the reaction shown in figure 9.1. This is an addition elimination reaction. Okay, you have to remember this addition elimination reaction. Okay, and why we will show next part. Addition elimination. This is addition elimination reaction. And why this is addition elimination reaction? This is shown by mechanism. Okay, and it also told you to complete the mechanism of the reaction between cyclohexylamine and ethanol chloride. Okay, RNH2 is used to represent cyclohexylamine. Okay, include are relevant lone pairs of electrons, curly arrows, charges, and partial charges. Now, this lone pair on this nitrogen will attack this carbon. Why? Because this oxygen is more electronegative, so it will attract electrons more. So it will be a partial negative, and it will form carbon will form partial positive, and this partial positive carbon is attacked by this ammonia and lone pair ammonia or lone pair of nitrogen in this cyclohexylamine. So it will form CH3 C O, and it will have a negative charge Cl, and this cyclohexylamine will be attached. Okay, this will be this is your intermediate. Okay, now this intermediate this chlorine is more electronegative, so it will uh, uh, attract electrons more, and this uh, charge on this oxygen is again will form this carbon double bond. Okay, so then you will have this compound L. Okay, L will form. So you can see that in this intermediate, this group cyclohexylamine is attached, added. Okay, so this is your addition. Then in this second step, the your you can say Cl group. Okay, HCl is eliminated. Okay, HCl is eliminated. So in first step there is an addition reaction, because there is only one product form, and then in the second step there is an elimination reaction. So that's why the mechanism of this reaction is addition elimination reaction. Okay, moving towards part The reaction between cyclohexylamine and an excess of ethanoyl chloride forms compound M. The compound has a molecular formula C10H17 and NO2. Then suggest and draw the structure of M. Okay. Now excess of ethanoyl chloride is used. So when excess of ethanoyl chloride is used, this hydrogen will also react with ethanol chloride, and diethanol chloride will this hydrogen will also remove and it will form amide linkage. Okay, and tertiary amide will form. Okay, tertiary amide. So the structure of M will be like this. This nitrogen will react. Both hydrogens and the nitrogen will react. This. This is your cyclohexylamine. This hydrogen will also react to form PH3, and so this is your structure of M. If you count number of carbons, you will get 10 carbons, 17 hydrogens, and 2 O and 1 N group. Okay, so this is your structure. These things comes with practice, so practice is a must. Okay, and there you are done with this paper. I hope you like the video. If you have any queries, you can ask me in the comments. Okay, I will try to reply you very soon. And if you haven't subscribed my YouTube channel, do subscribe the channel, and thanks for watching.